tarde, todos e todas. Hoje é um enorme prazer receber aqui o professor William Yang, da Universidade de São Paulo. O professor William, então, ele teve sua formação, tanto a graduação quanto o doutorado em física, na Universidade de Fudan, em Xangai, na China. Experiência profissional, passou por diversos lugares aí, foi também professor lá em Ouro Preto, na Federal de Ouro Preto, foi professor também em Fundão, antes de se estabelecer aqui lá na USP. Trabalha aí primariamente com a física nuclear e agora, né, um pouco de gravitação, que tem feito já faz uns anos, gravitação, na atividade geral. E é sobre essa pesquisa que ele vai nos contar um pouco hoje. Então, professor William, muito obrigado aí pelo seu seminário. A palavra é da sua. Fica à vontade, sim.
Falando um pouco mais fácil, talvez, para nenhuma língua. So it's a real pleasure to be here, and many thanks for the invitation from Professor Libele and also the department here to receive me, and also this Professor Denise who bridged this invitation for my visit. So I really need to thank her also. So today I'd like to report to you some of the things that we've done during the past few years. Essentially, a few topics which are not entirely connected, but I try to sort of convince you that they are mostly related by the concept of quasinormal modes in the context of black hole perturbation theory. And the mathematical approach we're going to use is this green functions approach. And as one explicit example, I'm going to talk about a recent study that we submitted. This carbon number, which is small, that 2402, about this echoes and daytime tails and the Damour-Solodukhin wormhole. So this is essentially what I want to say. So this is primarily collaborated with Remy. Remy actually, as I will discuss, has been doing the similar topic in parallel, and more recently we start to collaborate, and also with Professor Wang and Professor Yue from China, some of my other collaborators. So as I said, I try to connect everything, glue everything together in terms of the notion of quasinormal modes. So I've tried to talk a little bit about this. And yeah, I just want to say, I think it's not entirely formal, so feel absolutely free to interrupt me just any moment. If anything is not clear, I try to explain to the point that I can. So feel absolutely free to interrupt me. Please do that. So I try to talk a little bit about the physical notion, the physical concept of this behind this quasinormal modes, which is in the content of black hole perturbation theory. Then I move on to talk about symptotic quasinormal modes.
Good afternoon.
Symptotic quasinormal modes, and this is a little bit new, which is known as spectral instability of the black hole quasinormal spectrum. Then I move on to discuss briefly the gravitational wave echoes and light echoes. This is a little bit of deviates from the mainstream, but is it there? And then this is an example. I will discuss a unified model, unified picture, which embrace both the quasinormal modes and the daytime tail of this DS wormhole. So this is the plan. So in first place, what is quasinormal mode? I think first, quasinormal mode is a rather general concept in physics, in theoretical physics. It is a sort of notion, approach to measure if a system is stable. For instance, if I want to say if this table is stable, I may try to push it a little bit. I say, look, it's stable, doesn't fall. So what does it mean? So I introduce a small perturbation to a system. It can be a purely classical setup, classical system. So with a initial perturbation, so I think we can employ the notion that we learn in classical mechanics. So I can try to reinterpret the initial perturbation in terms of a superposition of a lot of modes, which essentially harmonic oscillations. If I try to use a properly coordinate system, so these oscillations are essentially perpendicular, orthogonal, right, and mostly harmonic, right. So this is essentially come from a chapter in classical mechanics. It's small perturbation. But what we learn from classical mechanics is perturbations are normal modes in the sense that the frequencies are real values. But in reality, most of the case, these oscillations do not persist forever. They're not normal modes. In reality, in real world, most of modes are essentially they decay, they are dissipative. So if I try to push it, it will start to vibrate. But after a while, these vibrations disappears. This is because the energy goes away. In this case, is because there are some sort of friction. So the mechanical energy turns into some other form due to the friction. So this is kind of typical example. I think in most of the cases we learn from a kid. As a kid, we know that most of the system is dissipative. So this is one way why system is not conserved, entirely conserved. In the context of gravitational wave, which is the focus of the presentation today, so energy is also not conserved. But in this case, it is in terms of the waveform, so the energy goes away through spatial infinity. So if you look at a system, it starts to emit gravitational wave, so the energy goes away. There's not a friction kind of type of thing which is happening, but the waves, in terms of wave, the energy is leaking from our system. So in both cases, by the end of the day, instead of a real frequency, we'll have a complex number where the imaginary pattern frequency measures a decay process where energy goes away. So this is essentially the picture of quasinormal modes. Mathematically, you can think of solving for the quasinormal modes as solving for the eigenvalue of a Hamiltonian, so a kind. Except you don't get the real modes, because in this case the Hamiltonian is not Hermitian. So we don't have this the sort of mathematical properties that we learn from linear algebra and quantum mechanics. In those cases, if you have a Hamiltonian, which is Hermitian, then the eigenvalue must be real. It's not a case if you have a system which is open system, which doesn't conserve energy. Okay. Other than that, you can essentially view and solve this problem as a eigenvalue problem, except you have a particular boundary condition. In this case, the wave goes, the energy leaks away through those outgoing waves. So this is more or less the physical picture I want to say. So in this slide, I try to emphasize quasinormal mode is essentially classical concept. You don't need quantum mechanics or other things to have this. It happens in all different kind of systems, but it's a classical concept. It does have quantum implications in the case of particularly black hole quasinormal modes due to this ADS-CFT threshold is different here. But in the context of black hole quasi-normal modes, it's an important concept that not the thing that I'm going to emphasize today. And I want to say this the rich physics here, and I'm going to mention a few of them, try to mention a few of them today. On the mathematical perspective, so we end up usually with a second order ordinary differential equation. It's ordinary because usually you can try to use a appropriate coordinate system, so one dimension is really relevant, and the remaining dimensions, they can be simplified due to the symmetry of the system. It's second order because of this Holatsky instability. So most of the system, we end up with the equation of motion, which is second order in time. In the context of black hole physics, so we need to discuss a number of equations, and typical example is the Ridge-Wheeler effective potential. I also don't want to go into detail of this. I just to flash you what is this, and let's consider this a typical, let's say, symmetric, chargeless, non-rotation black hole, for instance, and the simplest black hole possible, and let's discuss this. The focus is actually the quasi-normal modes and later entire echoes that I'm going to talk about. So let's do not go into the detail of this. And what is making the difference actually is the boundary conditions. I'm going to talk a little bit more. So the mass equation, which is the equation governs the quasi-normal modes, that's the Schrodinger equation that you're going to solve for the eigenvalue, which is the complex frequency. Basically looks like this. And this is already done in a particular coordinates called tortoise coordinates, but it's not focused here. This is the frequency you're going to solve, and there's a potential. So for a particular black hole, typical one, the most typical rudimental one is known as Ridge-Wheeler potential. It has such a form. The only thing we need to know in the context of black hole, so instead of a potential well, which we usually solve for the eigenvalue problem in Schrodinger equation, this is a potential barrier. Okay, so it's a bond in the middle. So the boundary condition corresponding to the wave goes out in both directions, which doesn't vanish if you go to spatial infinity. So those waves will carry energy flux in the sense that energy is not conserved. So of course, if we're solving for a boundary condition of Schrodinger equation, so boundary condition is different. You have the wave vanish at both ends. In this case, you don't have flux. That actually guarantees that energy is conserved. If you have energy flux, so it's intuitive. I think so. That things become different. So if there's a eigenstate, or it's a normal mode of the system, sort of quasi-normal mode, as we call it, it's corresponding to a sort of resonant state in quantum mechanics, so field theory. And in the context of black hole quasi-normal modes, there's a lot of different approaches. I definitely don't have the time to go through these. The focus we are going to use today is the green function approach. Essentially, from the mathematical perspective, I would say we try to analyze the singularity of the green functions and poles and branch and cut, and say, okay, those things are related to the quasi-normal frequencies, late-time tails, power law, etc. But this is not the only approach which use the analytical property of functions. Posh-Taylor one is another one. For instance, because it may have a very straightforward physical interpretation, so I want to mention this first as a is by another paper by Larry and Mashon. So they point out to solve for the quasi-normal mode, one thing they can do. This paper primarily know is they do a sort of wick rotation space coordinate onto the imaginary axis, so you can solve for the things. But the thing I want to mention is quasi-normal modes here corresponding to the singular point of the transmission coefficient, because instead of if we go back to look at it, you can say this is eigenvalue problem, but you can also say this is a potential barrier. So this is a scattering problem. So for a scattering problem, you can imagine you have an incident wave shooting at a potential barrier. So you have transmitted wave and reflected wave. And quasi-normal modes correspond to the case actually when the transmitted wave and reflected wave become singular. So the amplitude of these two become way more significant than the incident wave, to the point that you can simply forget about the incident wave. So you have a state which is sort of quasi-bounded here while emitting wave in both directions. And this corresponds a intrinsic modes of the system known as quasi-normal. So this is another way to look at what is quasi-normal. So this is the Hochschild approach, but the green function approach, which was first proposed by a couple of guys, Lieber, Noller, among others. But this is a paper cited here by Noller, 92. So he used this Laplace transform, but the main idea is this is because Laplace transform. So this is the imaginary of this S domain. This is real. So if you look at a green function, we transform you have a mass equation, right? So you can define the green function for this mass equation and transform this using Laplace transform and look at the things in the S domain, sort of frequency domain. And quasi-normal modes correspond to the poles of this green function. And besides these quasi-normal modes, there are possibly a branching cut. So there's a branching point here. And it's a custom to put the branch cut here for the Laplace transform on the negative real S axis. But this, we know for branch cut, you actually can put it anywhere. So the only thing is, if you use this to calculate any observable, you should get the same result. This is the only real requirement we have. So I would say this is just a custom that most people do this. If it's a Fourier transform, so this branching cut usually put on the positive imaginary frequency axis, and these quasi-normal poles are on the upper half of the compact thing. So if you look at a waveform, so you actually receive contribution from the poles because this is a frequency domain. So if you want to go into the time domain, you want to look at a waveform in time, so you will do the inverse Laplace transform. That is a integral along the parallel to the imaginary axis. You do the contour integral, so you will sum up you end up summing the contribution from the poles because of this Cauchy theorem, and also the contribution from the branching. And physically speaking, what's happening? So you have a summation of contribution from the poles. So each of these things corresponding to an oscillation with complex frequency. And this thing will give you, it depends, this is not straightforward from what I'm saying, but these things will give you another contribution from the difference from this cut, this contour, this part, and this part. And Actually, you subtract, calculate the difference, right? So this will give you a inverse power law in the as a function of time. The polynomial modes, they are unexponential due to the definition of the inverse Laplace transform. So you have something oscillates, but suppressed exponentially. This is essentially what happens when you push this table. It will start to oscillate, but the amplitude of the oscillation will increase exponentially in time. But this increase is governed by the imaginary part of the frequency, while the period of the oscillation is governed by the real part of the frequency. So you have essentially a oscillation which is suppressed exponentially in time. On the other hand, you have something governed by inverse power law. So that it is obvious that exponential suppression, which is faster, suppress anything way faster than inverse power law. So if you wait long enough, your quasi-normal oscillations will die out eventually because they're suppressed exponentially. So you end up seeing the contribution from here. So that's why you will always, if you wait long enough, if this branch cap exists, you will always see a inverse power law that's known as wave time tail. So another thing to mention is these polynomial poles are nothing particular at all, because if you open any textbook for quantitative theory, it will let you know that the resonance corresponding to a pole of the green function on the complex band, while any stable physical particle corresponding to the pole on the real axis, except this is Laplace transform, so it's end up on the imaginary axis. But that's essentially real axis for the Fourier transform, for the counterpart. Okay, so if we don't have polynomial, we have normal modes from black hole for some reason, so these poles should be all on this imaginary axis. But the boundary condition for black hole actually governs that any of these oscillations should be dissipative in nature. It would be actually strange if a mode never die out. It would stay on the imaginary axis and never dies. It would be very strange because energy is leaking while a certain mode is still bleeding. Like I push this table, it will start oscillating forever. This is weird, right? It never happened by experiment. Once you believe that most systems we encounter in the real world are dissipative, then this is mostly the reality instead of a stable pattern, stable mode. Actually, in black hole, there's no stable. Wouldn't be the case. So this is more or less the mathematical aspect of the thing I want to discuss. I think I took too long. I'll speed up a little bit. But here's another thing I want to discuss before I go to the example is the physical part. And that is, nothing I said is actually new. This has been known for decades, actually. But what I want to talk about, this is the physical aspect, is a little bit new. That's known as the spectral instability. And I'm going to try to promote this to you. Please, any questions, please stop me. Then, okay. So this is also started by a paper by Noller. This is quite early, actually, 96. So he did this. The name of the paper is Significance of Polynomial Black Hole. It's a very generic question he proposed. It is, so you have a black hole, good, and we have a bunch of approaches which can give you the polynomial mode, work perfectly. But in reality, black hole never be this perfect, symmetric, non-rotating, sort of chargeless object. You always get something else. You have a dust, which is spiral into the black hole. You may have a halo. You have a lot of things. The nature is never perfect. So in this regard, effectively, in instead of the rich Wheeler effective potential, you will have something else. You will have a small perturbation to your effective potential. But from a physical perspective, I would say it's following. Not, maybe not physical, I say from an observational perspective, I would say following. Why quasi-normal mode interesting? This is because if I measure the gravitational wave emitted from a black hole because of the quasi-normal mode, I perturb the black hole a little bit, I throw something into the black hole. It's an initial perturbation, so I receive some gravitational wave from the black hole. This is superposition quasi-normal mode. So I obtain a time domain waveform, then extract these frequencies. Those frequencies should be the black hole quasi-normal mode. And there's one thing known as theory of black holes. So the idea is, by measuring the gravitational wave, by extracting the frequencies, I will eventually identify what are the intrinsic parameters of this black hole. What is its mass? What's its charge? What's its, etc., etc. What's its spin? So this whole sort of, it's on the observational side, but this whole thing is known as black hole spectroscopy. This is relevant today because we're finally able to measure gravitational waves. So this is no longer a, let's say, theoretical speculation. Maybe 50 years ago it is, but today it's going to be measured in 10 years, 20 years at most, right? So we have to compare our calculations against the measurement in the near future. So it's actually something serious. So the idea is, again, measure the gravitational wave. I will eventually identify the black hole. This is called black hole spectroscopy. And not less that, look, no black hole is perfect. So that what in practice what happens is you don't have a perfect black hole. You have a black hole with some environmental dust, let's say. So it's known as a dirty black hole. So a measure the gravitational wave, yes, but it doesn't maybe correspond to a perfect black hole. So is it still possible? To what extent you can still extract those important parameters and the line parameters of black hole? So the answer is, the physical intuitive answer is, if I have this table which is stable, I put one thing on top of it, and I perturb it, I should get essentially the same thing, right? The frequency shouldn't change too much. Otherwise, maybe I would say, maybe this object is not observable. If I perturb it, but not the perturbation we just talked about per se, but I sort of perturb the Hamiltonian of the system a little bit, I don't expect the spectrum, the eigenvalue spectrum of the system will significantly deformed because of an insignificant amount of perturbation to Hamiltonian of the system. I would say this is intuitive, but you can try to give it a test. So now I did the calculation, but what I just said is actually what we try to understand today. But back then he did is, try to use a piecewise approximation for this effective potential. So this he introduced a staircase approximation. This is about, I'll read it to you. This is 1, 4, 16, 64, 256, etc. So this is maybe 16, if you can still see the difference apparently. But if it goes to 124 steps, you essentially cannot visually see the difference between the original regionally effective potential and your approximation. Even though your approximation are discontinuous function composed of small steps. But then for the second case, let's calculate the quasi-normal mode. So this is maybe not clear to you, so let me just imagine when I tell you. So for black hole quasi-normal modes, those modes actually the ground state somewhere here, and the higher order modes, known as high over points, climbs up with larger and larger imaginary path. Actually, it's negative, but with bigger values. So it's kind of climb up the imaginary axis. So it is not clear here, but because of the resolution and everything. So the black hole quantum mode goes up like here, like this. And all these things corresponding to different number of stacks knowledge introduced. So you can see, obviously, the entire spectrum becomes drastically different. Okay, so after that, that's a paper by Ramin that was way more recent, but that's tiny. So he did this. He say, maybe let's try some more smooth approximation, because if you have a stepwise effect of potential, it's definitely not a good idea, because of discontinuity may introduce some physically inconvenience and drastically change the system. Let's try something smooth. He still get the same result. Then after that, we tried, we did something more sort of abstract. We say, let's consider only one single step. And maybe we introduce maybe the effective potential is still continuous, but you introduce a discontinuity at even a high order into a modified effective potential. Then we calculate analytically the asymptotic modes, which are the modes corresponding to these ones. So the high order mode, high overtone actually. So it's what we did is we actually assume the mode has a significant real path. If this is true, we can show that its imaginary path is not as significant. In other words, the modes lie in parallel more or less to the real axis. But for black hole quantum mode, I didn't show this to you. I just tell you that the modes, symptotic modes, will lie up in parallel, essentially, to the imaginary axis. So there's a significant difference in the symptotic behavior of the quantum mode. Okay. So to sum things up, then it was in 2021. These guys actually, Rodrigo is Brazilian. I don't know him in person, but Rodrigo is Brazilian. They tried to generalize this and call it structural instability or spectral instability. So what they did is they tried to introduce some randomized but insignificant perturbations to the effective potential and calculate symptotic mode. So this is what they get. This is the case they introduced perturbation into the partial potential. So these two, the series of dots, they corresponding to the original quasi-normal modes of the partial potential. And these are what happens if you introduce a small amount of randomized perturbation. And I can read it to you. These different branches of dots and symbols corresponding to different magnitude of perturbation. But this magnitude is really small. It's 10 to minus 36. It's 10 to minus 5, 10 to minus 8, 10 to really, really small perturbations. But the entire spectrum are distorted. So there immediately, I don't think this implication of these results has been explored thoroughly in the literature today, because everything was proposed about 2-3 years ago. And I don't think these experimental guys already take serious concern and attention about this. And the paper is published along this line of thought. I'm not going to show you, but to me, this is the thing I want to tell you instead of the thing we did. I'm going to talk about this today. So this thing is known as spectral instability. It's a new thing in the study of quantum mode. Then just this I'm going to go a little bit faster. So what is gravitational wave echo? Gravitational wave echoes is a thing proposed by Cardozo and his collaborators. Because if you want, again, black hole spectroscopy, and so you measure the gravitational wave, but their argument is the following: if you have black hole, if you have a wormhole, if you have a compact star, which is not a black hole, but if the star is really compact, you still do have significant, let's say, redshift. It's not infinite, but really significant. So we know for black hole you have infinite redshift. So, but if you try to measure this, so it will be very difficult for you to tell the black hole apart from other sort of compact stars. And then people say, okay, I can measure quasinormal modes. The same. Their argument saying the quasinormal modes will be similar. Essentially, their argument trying to say it will be practically difficult to do the black hole spectroscopy. So in this regard, black hole echoes were proposed saying, okay, actually these wave signals might echo. And this will play a vital, essential, it can be used as an essential observable to tell apart different compact objects. So this is what black hole echoes is. So what I want to say is we actually show these echoes are related to a branch of asymptotic quasinormal mode. When we published this, we were not aware of spectrum stability. This was 21. So we just call it novel spectrum quasinormal. But today we understand this is coincides. This coincides with this high overtones related with the spectrum stability. They are essentially the same thing. And black shadow is also a thing if you have looked into the news. So this black hole image recently, already a couple of years, published. And I just want to skip this, but I want to say this is also related to the quasinormal mode. Intuitively, it's not. Black hole shadow is related to you calculate geodesic and you evaluate black hole shadow or black hole image. Had nothing to do with quasinormal mode. It does, because what is geodesic? It's the trajectory of light. So what is light? It's electromagnetic perturbation. So if instead of doing it geometrically, so like calculate the geodesics, you do the thing from scratch. You study the electromagnetic perturbation. So there's argument saying there's one thing called the black hole glimmer. The black hole shadow is in the space domain. If you think of time domain, there's argument saying the black hole glimmer, and it is actually related to black hole shadows. Both things, they just the spatial and temporal aspect of the brain function. They come from the same sort of dynamics of the theory. And these things can be contributed to the symptotic mode. Now let me briefly discuss this is a recent archive preprint about late-time tail in DS type wormhole. First, what is late-time tail? Late-time tail come from the branching cut. So bear with me, but I mentioned a bit of this technical detail. So what is the novelty here? So most of the calculations people have done regarding late-time tail, particularly for black hole, you don't consider any singularity in the ingoing wave. You need ingoing wave because you need an ingoing wave and outgoing wave to construct the Green function. You have a mass equation, so you can construct Green function by considering the ingoing wave of the corresponding homogeneous equation which satisfies the ingoing boundary condition, and outgoing wave satisfying the outgoing boundary condition from the correspond to the homogeneous equation, then you can construct the green function. When you have the green function, you can discuss the singularity if there's a branching contain this, so you can evaluate the late-time tail. But in most of the calculations in the literature, people don't consider any singularity in the ingoing wave. That makes sense because there's good reason for that. Except if you consider wormhole, you do have singularity because the ingoing wave in a wormhole actually is the outgoing wave in another universe, let's say. So it does, almost by definition, contain some singularity. So why this will change anything? But because if you have both waveforms have singularity, so go ahead and evaluate the contribution from both sides of branch and calculate the difference. Find why it's different. The difference is following. As a matter of fact, if you want to evaluate this, you have to evaluate the Wronski. When you do this, it's not straightforward to evaluate. The most convenient way to do that, you pick a point where you know a specific form of the outgoing wave. And this point, special point is the point where the inner path, let's say, of a black hole, where you don't actually care about what is the spectral form, the potential, what's the form of the waveform. It doesn't matter because only the singularity will enter. So you can pick that point so that the point is common for the waveform on both sides. So you can evaluate the Wronski. Because Wronski doesn't depend on the spatial coordinates. You can pick any. But except you pick a point on the outside, you don't actually know what is the waveform corresponds to the inner path of that hole. So the most convenient way, actually, single point which is convenient, is the point of intersection. Except in the case of wormhole, you don't have this convenience because you have a stroke, which is in the middle. This is a very simplified toy model of a wormhole, but it suffices for the mathematical purpose. So you have a stroke in the middle, but to evaluate the Wronski, you actually cannot do what has been done here. So you actually maybe pick one point which is in the section of the throat and the outer part of one universe. But then the singularity comes from the ingoing wave, doesn't take a path. So by the end of the day, you can introduce an effective renormalization to the waveform, which carry exactly the same singularity you need onto the point that you evaluate the Wronski. So this is a sort of technical detail that we introduced. So that's the part of novelty that we have in this for the late-time tail. For the echoes, there are two different approaches actually on the market. Both are very nice papers that we learned a lot from them. One from, I can cite them here, one from Mark, the other is from Brano. So one approach, people use the green function. So they explicitly calculate the green function if you have a compact object, and because it's a compact object, it's not a black hole. So you can imagine on the surface of the star, the compact object, you have a reflection coefficient, because the wave incident onto the surface will get reflected. The specific form of this reflection coefficient depends on the particular type of star you're talking about. But actually, that doesn't matter. You can just simply assume a rather generic form. The only thing you really need is a length scale. Because echo, what is echo? Echo is something bounced back. So by definition, there's a length scale which governs the echo period. Right? In this case, that is the surface of the star and a particular point, a typical point of effective potential. So the distance between these two points will govern the period of the echo. This is one approach. The other approach is introduced by Bueno and his collaborators, and they didn't use green function, but they calculate the transit matrix and try to extract the quasinormal modes from the singularity of the transmission coefficients I just mentioned. And in that way, they actually point out echo corresponding to a different branch of quasinormal modes, entirely independent of black holes. The only thing about these two papers is, even these two papers mention the other approaches entirely equivalent, but if you put them together side by side and try to compare, this is our point of view, they don't. Okay, there's some technical detail that you have to refine to confirm these two approaches actually consistent. The physical maybe insights of this is, if you want to calculate the reflection, say, assume a reflection coefficient at a certain point. But if this point is rather generic, it's not a particular point. The point doesn't carry any physical information like a particular star. That's the case. So we definitely need, requires our final result doesn't depend on the choice of the spatial coordinate of that point. Otherwise, the calculation doesn't make sense. The calculation shouldn't depend on an arbitrary point that you choose to evaluate the reflection coefficient. So in this case, if you put these two approaches together, I strongly invite you to read our preprint. There was discussion about if you try to see a rather consistent picture of this approach, there's this detail you have to pick. So this is on two sides. One is about the echoes, the other about late-time tails. Then one novel piece we add to this is both of them are considered as late-time phenomena. As I mentioned, the late-time tail corresponding to a inverse power law decay, which is slower than an exponential decay. So when the polynomial modes die out, the inverse power law will always survive. That's the late-time tail. It's a late-time phenomena on one side. On the other side is echo. Echo is also a late-time phenomena because you have a length scale. It doesn't happen instantly. You have to wait for a typical period of time for echo to be triggered. Then there's a sort of fine-tuning in this, because if you do have a echo which happened too late, you wouldn't see this. You wouldn't be able to measure this because everything has decayed too much. You don't have enough strength in your signal to get measured. And if, on the other side, if the echo happened too early, happened almost immediately after the emission of the quasinormal oscillations, then you won't be able to the late-time tail because echo primarily overwhelms the late-time tail. This is essentially why to our understanding, in the literature, both of these things have to be discussed, particularly in the context of Damour-Solodukhin wormholes. It has. But none of the paper discuss late-time tail mention about echoes. None of the paper discuss the echoes, talk about late-time tail, neither in their numerical calculations, because they were not aware of the other thing. And so what we show is it is possible if you choose a particular parameter that may happen. So this is late-time tail. It's in the log scale, so it's a string line for inverse power law function. So this is string line, and this is echoes. If you show this, this is log in the time scale, but if in linear scale, you see it is periodic echo signal. So there's a good reason to say these phenomena may happen by taking physically relevant parameters. So this is essentially what I want to say. I think I have to take a bit more than supposed to. So this is the concluding remark. I do this briefly. So thanks a lot for your attention.
what is the stability or instability in black holes? I'm not familiarized with this.
Black hole is stable. This is one thing actually attributed to Stephen Hawking, right? So he has this thermodynamics of black holes. So you have Zero's law of thermodynamics. Zero's law of thermodynamics means, I think in the context of thermodynamics, the system goes to a thermodynamic equilibrium. So you have the notion of temperature. We have. So it's very difficult to prove, but in the context of black hole, actually, to a certain way it was proven. But in the context of thermodynamics, we just simply believe this, right, by our daily experience and everything else. So we know things get thermodynamically equilibrium. So if you apply this to black hole, which says black hole does equilibrium and it is stable.
Thank you very much. Is there any other question?
Why is it important studying gravitational for snow waves and have some application?
Because gravity is because there's 4 types of, this is rather, maybe it's not what you asked, but there's 4 types of interactions, right? So gravitational wave is, a couple of years ago, it is the only type of interaction we don't have direct evidence of its existence. Okay? So in terms of measurement, that's the only piece that was missing. So of course that's important because you have electrodynamical interaction and we have electrodynamic radiation. So similarly, if it's gravitational force, so if that's a type of interaction, and it's equation motion also as mentioned second order, so it's natural to expect it has a waveform. So that sort of existence, sort of say that excitation, still not graviton, but sort of solution, plane wave solution was not verified until very recently. That's just because the theoretical curiosity that's already important in that sense.
Any other question?
I do. You mentioned that the frequency has to be a complex number for it to be the leak of energy. Is this in any way related to the continuity equation associated with the Schrödinger equation? In the sense that if the frequency was a real number, when you calculate the continuity equation on the right side of the equation, you would have a 0. And if this is a complex number, you would have a source or a term that absorbs the flow associated with the Schrödinger, with the wave function. Can this be thought in this manner?
I might be wrong, but I think the conservation of flux is not affected by the fact that the frequency can be complex. You will still have the conservation of flux that works essentially the same equation that you will have.
But in that equation that you showed earlier on the beginning of the seminar.
Yes, the mass equation is.
Where is it? Yeah. Wouldn't it lead to the non-conservation flux if the frequency is a complex number? I'm really asking for a curiosity more than anything.
I don't remember the specific detail at this point, but I do remember the flux conservation is not affected by
this one.
It's not affected. Right. Let's say before this is already you are talking about. Let's talk about a particular waveform with frequency W to have this, right? Before this, you have a partial differential equation in space and time.
Right.
So your flux conservation comes from that.
Oh, okay, yeah, true.
Right.
This is not time. Yeah. So sorry. Yeah, that makes sense. Yeah, this is only a spatial equation, right? Right. Thank you.
Any other question? So it's my turn. quasinormal modes. Every now and then I hear about them, but I never study them exactly. So I just want to get the physical picture behind it. So you have a black hole, and then you perturb this black hole, and then you essentially analyze this perturbation, and you're saying that this mode then dies off rather quickly. Is that it?
Yes. It's the same as it's a table, you push it. So you study the temporal evolution of this displacement of the table. You realize this can be written as a superposition of harmonic oscillations, so except it dies, the amplitude dies in time. So there's a discrete frequencies there, it's not continuous.
And what's the source for the frequency?
So in this case, you consider the initial perturbation as an initial condition of your equation. Because you have this initial perturbation and you leave it, so it's pretty okay. You can define it as a Cauchy problem. So because after that you leave it, right? If you have an external force and doing this forever, then you have to consider external force, which will be present on the right-hand side of it.
But then physically, what you have in mind, like some astrophysical source,
yeah, anything. That's you throw your shell into the black hole. That the moment you leave your shell, that's the initial condition, right? You don't like the dynamics govern how the system evolves. You have a halo. Halo usually always get absorbed gradually by the central black hole. This is more or less.
Right. Just another question. Could you also have some mode that runs out, like goes to infinity? So on one hand, you have this mode that dies off, but
dies off. They also both of them. The wave actually always go down. So you have black hole actually because this equation is radial coordinate. So the outgoing wave actually is the going wave going out radially and even symmetrically, not necessarily symmetrically, but you can imagine this. So it goes radially outward, goes to infinity, leaving the black hole. And there's an ingoing wave, but because this is radial coordinate, so corresponds to the wave get absorbed by the horizon of the black hole. Right? So any quasi-normal mode actually corresponds to the things escaping, sort of leaking, gradually leaking.
My question is, could this wave blows up?
Yes, when you have a mode blows instead of suppressed in time, we would say, look, this black hole metric is not physically relevant because it's not stable.
And that, yes.
Then you cannot have this interaction. You cannot have this black hole solution. The theory, the modified theory of gravity is wrong because look, it has a mode which is not physically relevant.
And that's a problem.
Usually you directly you say the theory has some problem, but usually people don't like that.
Okay. Any other questions?